So good morning. We have been doing in the last week, importantly, what are called steady state gain. What do you mean by steady state gain? As far as lateral dynamics perspective is concerned. So you are able to use those steady state gain as metrics to compare the vehicle handling characteristics of different vehicles. That is an advantage of having the steady state gains. So three important steady state gains are yaw velocity gain, lateral acceleration gain, and curvature gain. So these gain values are the values which were obtained from the transfer functions as s tends to 0. That's what we have seen. See, when you say transfer functions, these are an important element in control design system. Control design requirement for the vehicle system. Because basically your vehicle has to be acted upon a closed loop control system. As far as that, if you concern with the autonomous vehicle today, your vehicle has to be more and more intelligent. So whatever the driver will give an input, and the driver used to correct the input according to the output observation. So if a driver has to take a turn, right turn, and go in a course, so the vehicle has to go in a course as he does steering, right? Variation in steering angle. So if it doesn't do, and then there is a problem. So then what is that is required is there is a requirement of correction in your transfer function. That means what is that output that you get for the given input is not appropriate in the system. So that has to be proper. What I mean by that, if any system can be checked with some standard inputs, right? If I give some step input to my system, and I should get an output also as it is a step output. If I give a harmonic excitation as my forcing function to the system, I should also have to have my vehicle to behave in that similar fashion. So that is what is called a steady state motion. So the input what you give, it responded in the similar fashion as an output, and you see that it is reaching the steady state. But in between, you see there is a transient scenario, transient state, and after that it will reach to the steady state result. So if your vehicle has to get the steady state gain, it takes some substantial duration, and that is what we refer to time tends to infinity, whereas the equivalent is s tends to 0, so that in your transfer function, from the transfer function, you are able to get your steady state gains. If these gain values are there, we have seen their physical interpretation in the last class as function of what is that you have drawn all the steady state gain, you have drawn as a function of forward speed, right? Vehicle forward speed. So you see that vehicle forward speed at different speeds that you are doing it, right? It was used to compare the different vehicle handling performance. So in short, if you want to say, we could witness that from these gains values, all the three vehicle tendencies during cornering, those tendencies are neutral steer tendency, understeer tendency, or oversteer tendency. So we could see that the behavior of understeer tendency is the least responsiveness. See, when your vehicle is behaving to be a neutral steered condition, it is very responsive, as well as responsive nature vehicle for your handling characteristics. Correct. In case of the value of understeer gradient existing as positive value, you see your vehicle behavior is less responsive, least responsive, because it is going to predict us as an understeer effect. If your understeer gradient value is negative, the vehicle is turned out to be an oversteered tendency vehicle, where it is most sensitive vehicle. So you see that if neutral steer vehicle will have KES value 0, that is a very responsive vehicle. If your KES value is more than that of neutral steer KES, that's zero value, that's positive value, then it is least responsiveness of the vehicle. The more and more understeer effect of a vehicle is least responsive. That means that steering effort should be more to be given to bring your vehicle turn in the or its maneuver in the curvature under moderate or high speed turns. Whereas on the other hand, if you have KES value negative, you see that it is most sensitive, because that speed may become a critical speed wherein you would not be able to have the vehicle stability. So the vehicle can enter into a state where there is without any steering input, your vehicle would spin about vertical axis. That's all we have seen. So vehicle should not be more sensitive to oversteer as well as least sensitive to understeer effect. So there should be a compromise. So that is on one hand. Also on the other hand, if you look at this vehicle handling characteristics depends upon different operating condition of your vehicle. We have been looking at a simplified model, that is our bicycle model, where you see from the vehicle itself, we do not differentiate the vehicle mass as sprung mass or unsprung mass. We have all together, as we do not consider suspension in our bicycle model. So there is no effect of roll during turn, right? So if there is a effect of roll during the turn, there is something called a roll steer effect in your vehicle. That is called a transient effect in your vehicle. So what is that roll steer effect? When there is a roll of sprung mass with respect to unsprung mass, there is a steering effect in your wheels, and that is what is called the roll steer effect, right? Similarly, if you look at, there's something called compliant steer. Compliant steer, what is that? It is a relative motion of one unsprung mass with respect to sprung mass because of some bushings that are there in a mechanical system, particularly on suspension steering mechanisms. So that would create some kind of steering effect, and that is what is called compliant steer. So that is also something kind of transient effect during hard cornering. If you look at something called camber steer, so camber angle variation also would be there, as the motion of your sprung mass relatively happening with respect to unsprung mass, you have some steer effect on your wheel, apart from the steering that is given by the driver through the steering wheel, right? So if you do not give, see, sometimes we do check that is my camber, everything is perfect. We take out our hand from the steering wheel, what will observe a vehicle, is it going in a straight line? So in case it is not going, or suddenly there is some variation, that is all called a transient effect. That transient effect can come due to this kind of roll steer or compliant steer or camber steer and so on. So these all are some of the important practical real-time operating conditions. You also have some design aspects is concerned. So what do you mean by design aspects is concerned? So we have different tires. So if you look at this understeer tendency or oversteer tendency or neutral steer tendency, is basically depends upon the loads in the axle and the cornering stiffness of the tires. So these are the two things that we have looked at predominantly or only consider in bicycle model, right? In case you incorporate suspension, other thing, these additionally whatever that we have been discussing on these roll steer, compliant steer or camber steer, all will come into picture. That all we will see separately after CAT 2, looking at the improvised model of your bicycle model, or eliminating the assumption of suspension not considered in your bicycle model. If we account your vehicle with the suspension and discretize your vehicle mass as sprung mass and unsprung mass. What do you mean by sprung mass and unsprung mass? Total mass of the mechanical system about the suspension, whatever is there in your vehicle, are called sprung mass. What all there below the suspension, that is axle, tire, wheel assembly, all put together, is what is called an unsprung mass. So the suspension will bring the flexibility in your vehicle, and that is going to cause the variation in your understeer gradient value. Whereas in bicycle model, we do not consider suspension, so it is only depends upon the normal loads in the axle and the cornering stiffness in the cornering stiffnesses in the tires. But this cornering stiffness also in our bicycle model, we consider to have as a constant value, linear model. C alpha F and C alpha R we consider to have a linear value, constant values. Whereas in reality, the tire cornering stiffness function of normal load. Right, that we have already discussed in module 1 when we have learned what are the properties of tire for handling characteristics. At that time, we have looked at in detail what would be the effect of cornering stiffness as the normal load increases. So in order to define that, we define something called cornering coefficient, which is ratio of cornering stiffness by the normal load and the axle. So this cornering coefficient would decrease as the nominal load percentage increases. So these are all something that we have seen earlier. So if you look at radial tires and bias ply tires, radial tires are more stiff compared to that of bias ply tires. So if I have my vehicle, all tires are radial tires, that's fine. Supposing I have in front axle radial tires and rear axle bias ply tires, again you see the stiffness values would be different. That would have an effect on your vehicle handling characteristics. So like that, if you keep on looking at the vehicle design aspects as well, apart from different operating conditions, so they are all responsible for the variation in vehicle handling characteristics. So what are some other design aspects? You can have a vehicle of front engine, front wheel driven vehicle, or rear engine, rear wheel driven vehicle. So if you see their handling characteristics are going to be different. Of course, the inflation pressure is another important aspect. So if I reduce the inflation pressure of the rear axle, so the cornering stiffness of the rear axle will be reduced compared to that of front axle. That would again have an effect of oversteer effect. So originally the vehicle is of understeer vehicle can be changed into an oversteer effect. So like that, if you see, there are various design aspects of the vehicle and the operating condition of the vehicle are very important, and they would actually change the effect of vehicle handling characteristics. So though the input is given to the vehicle by the driver, correct steering, but sometimes these effects are going to influence on the value of KUS, and the KUS is not only depends upon normal load and the constant cornering stiffness values. So this has to be kept in mind. So this 5 minutes discussion what we had are very, very important. In case you have a doubt, please revisit to this video lecture and listen to that back. So there are many parameters. So in such cases, what are the ways to analyze, ways to predict our vehicle handling characteristics? That's where you see an advantage of conduct of vehicle test and doing some real-time measurements. Whereas in bicycle model, though the model is very good model in order to study the vehicle handling characteristic in two perspectives. One is directional control aspects, another one is directional stability aspects. So these two conditions to study, we can have a simplified model like bicycle model, and then we can improvise that model by incorporating suspension into it and so on. But however, these models are good models so that we can have with the realistic assumptions imposed, stating that I would neglect the transient effects. However, I would always drive my vehicle with the constant forward speed. The effect of gradient variation due to transient effect can be neglected. If you make such kind of assumption, whatever that real-time operating conditions can be simplified, and that would give you a quantitative assessment of your different vehicle behavior during cornering. Whereas in order to authentically to state, we require also some handling test. So today's class, we are going to look at such kind of test and what are those and what measurements are required. How can we interpret the vehicle handling behavior? So those tests are basically steady state test. So what I mean by steady state test, my vehicle forward speed should be same. That means during maneuver or during my test, I should not apply driving torque or vary the driving torque, or I should not apply a braking. So you know, when you apply traction or braking, what would happen, right? That is also going to create some kind of transient understeer effect. So instead of steady state cornering, if I have my cornering and I suddenly apply acceleration, traction, what would happen? My load of the vehicle would transfer from the front to the rear. That will in turn will change, increase in the slip angle of the front axle wheel compared to that of rear axle wheel. So the vehicle would behave more of understeer effect. On the other way, if I apply braking, a vehicle which is originally an understeer tendency vehicle can change its tendency as the load transfer is from the rear to the front, and the rear axle wheel slip angle would increase compared to that of front axle wheel. So these are all something that would happen in a short duration, or time tends to zero, that would be dying. That's what time tends to zero or time tends to infinity. There are two conditions that you look at whenever you are looking at the time responses. So time tends to zero means there is a settling time where this transient effect will go out, and you would have your steady state response. So we would have a separate lecture on looking at first order system, second order system, what do you mean by transient effect, steady state effect, and so on. Right? That would help you to look at your reading the journal paper or understanding control strategies behind your vehicle handling and so on. So with this background of discussion, I think that you're been motivated to understand today's lecture on various testing that are going into characterizing the vehicle behavior during cornering. So let me just share my screen and quickly look at what we did in the last class and continue with the today's class. So if you look at last class on lecture number 27, we were looking at this steady state gain. Of course, I did not straight away derive or put the steady state gain. We looked at vehicle transfer function and what do you mean by frequency response function, and then we had come to steady state gain. There's something called transfer function, very important, that we will see that how can we get this transfer function from our state matrix and so on. Very interesting. We will see them in the coming lectures, right? And these are the three important gains: yaw velocity gain, and lateral acceleration gain, or curvature gain, that we looked at, and their expressions are derived using the Camber rule. From there to get a transfer function. From transfer function we got your this one, equation 3a, right? What is called a steady state gain, putting s tends to 0, right? A similar fashion we could get other gains, and we were looking at the variation of this yaw velocity gain as function of speed. And you see that we discussed on that where we were able to define characteristic speed as well as critical speed and so on, right? And similarly, other two gains also we have derived. One is the lateral acceleration gain and another one is curvature gain, and these physical interpretation also we discussed in the last class. And today's class we are going to look at importantly testing of handling characteristics. So this is lecture number 28 and 29, and today's date is 12/4/2021. Testing of vehicle handling characteristics. This is the title for today's lecture. So there are various tests that can be conducted correct? Why this test is what is because to account variation design aspects of a vehicle as well as variation in operating condition of your vehicle. So when you have to consider this, and these tests are conducted on a real-time vehicle and do some measurement, and you will be able to talk on this vehicle behavior, right? So what is that the main objective of such test? Is to predict the vehicle handling behavior of the road vehicle under steady state condition. So we are going to look at a steady state condition, right? I'm trying to write clearly. In case you do not follow anything that I write, please stop me. I will recorrect. So these steady state conditions means, correct? I am not going to vary my vehicle speed, right? I am not going to accelerate or brake during my cornering. My vehicle parameters are not going to vary as function of time. So what are my vehicle parameters? What are my vehicle parameters? So vehicle parameters, when you say responsive parameters or responses, R1 is yaw velocity, lateral acceleration, and curvature, right? Or third one is curvature. So what I mean by curvature is 1 by turning radius. Or you can also say instead of curvature, turning radius. So these are all important vehicle response parameters. Vehicle parameter, when I say it is a wheelbase, geometrical parameters. Those are called not a response parameters. Those are called geometrical parameters. What are called wheel base, which is L, and then maybe steering wheel angle. Another one is called the steering angle. So what is that difference between steering angle and steering wheel angle? So steering wheel angle is that angle that is given at the steering wheel where the driver holds the steering wheel. Where steer angle generally refer to the wheel plane tilt with respect to vertical axis. So steering that is going into the tire wheel assembly. And the subscript F refer to front axle steer angle. Front axle wheel steer angle. That is what is. So these are geometrical parameter. Geometrical parameters. Of course, the weight of the load of the vehicle. You can also say WF and WR. These are all comes under the geometrical parameter. Vehicle parameters, when I say it is by default response parameters. These are all that we look at it during cornering, right? So if we have that, now these tests to conduct, we would do this on a standard test track called the skid pad. So what are called the skid pads? So skid pads are very long, right? Which are a very large test track with the flat surface and paved area. So it is a large, flat and paved area is what is the skid pad. So vehicle can go in the skid pad and it can have different tracks of various radius, tracks of various radii, so that I can have different radius test and so on, right? So this is what is called a skid pad. So on this skid pad, you would be conducting steady state test. So there are three important tests that commonly conducted. What are those tests? So test number one is constant radius test. So what do you mean by constant radius test? So I have my skid pad of constant given radius. So my that would be a circular track. So constant radius test is a circular track. So your vehicle has to go with the different speeds on this circular track. The vehicle is driven along this curve with the constant radius, along with this curve of constant radius at different speeds. So the test at different speeds. So what do you mean by different speeds? It is not you are going in this with an acceleration test, like you are entering the circular track and you keep increasing your throttle, and then what is happening? Your speed is increasing. You are not doing that. That's not a constant radius test. So in constant radius test, you are driving at different speeds. So before entering the circular track, you would have a path where you would accelerate your vehicle, take the vehicle as it enters the circular track with the particular speed, complete the lap, and then come back. Again, when you enter, we have the different speeds. So like that, at different speeds, you would be conducting in the circular track. Then only it can be a steady state test. Otherwise, it is not so, right? So that is. So what do you mean by that? As you enter with the constant speed in the circular path, the measurement starts. But to enter with that required speed into the circular test, say I have to enter as 100 kilometers per hour speed and I have to maintain the speed in a circular track. I can't just reach 100 kilometers per second as I enter and then. So before that, I would accelerate my vehicle from start till that 100. Maybe it takes some few seconds to reach for a vehicle, and then I would hold the speed and conduct. And then hold the speed at 90 kilometers per hour, 80 kilometers per hour, and like that I can have. Either I can go with the higher speed and have reduction speed, or the other way, increase the speed gradually in every circle test, and then you take the measurements. So what measurements that you are going to take? There can be two measurements. So one is steering angle, of course, steering angle measurement. So you have to measure your steering angle. What is that you are giving for the vehicle? Correct? You have to measure steering angle. So these are measured. What are measured? So steering angle. Another thing is lateral acceleration. So the lateral acceleration, to measure, you require an accelerometer. Or you can measure, instead of lateral acceleration, you can also measure yaw velocity. So to measure an yaw velocity, you require a gyroscope, rate gyro sensor. It's called rate gyro sensor. So if I have rate gyro sensor, I can measure yaw velocity. Or if I have an accelerometer, I can measure lateral acceleration. So one thing that you should understand, there is a relationship between this AY and your yaw velocity. So what is AY? It is U squared by R. Newton, it is meter per second squared. If I have AY given in terms of G, I should divide this in terms of G, right? So this is your lateral acceleration, U squared by R. From kinematics that we also have seen, I have yaw velocity or yaw rate, it is multiplied by turning radius is what is my forward speed. What is my forward speed? So what is that? I have R is nothing but U by R. So I can also state that my lateral acceleration is nothing but R into U, right? Because U squared by R, where U by R is R, so R into U. So it is product of yaw velocity into forward constant speed is what is my lateral acceleration. So what does that you understand from this relationship? If I have measurement of AY, I can also have what is my yaw velocity. How do I get? Simply divide your lateral acceleration measured by the forward speed. That's all. Or if I have my yaw velocity measured using rate gyro, then I would simply get my lateral acceleration by multiplying it with the forward speed. So that is my AY. So this is coming from your kinematics of your vehicle geometry. So with this understanding, we would proceed further. So what is that measurement that you make is steering angle variation as function of lateral acceleration. So let us consider now that variation when you measure, how that would be when I plot the data. So I have here my steering angle. So maybe it is delta F, and that as a function of lateral acceleration AY. I normalize that by G because that is the way in vehicle industry. Your lateral acceleration or longitudinal acceleration all are represented in terms of G's, right? So normalized value. So divide that by 9.81. So you have this. So if I take it like this, then you see now my measurement would appear something like this. So before that, let us look at what does this test? Steady state test. So steady state test motion is governed by the equation delta F is equal to L by R plus KUS into U squared by GR. So this is what we have seen already as a fundamental governing equation for steady state motion. So in this now I have got so you can rewrite this as what L by R plus KUS, and U squared by R is what is AY. So AY is lateral acceleration by G is what is delta F, right? So this is my governing equation. So if your vehicle happen to be of neutral steer vehicle, right? What do you mean by that? You go in this constant radius test and you see that you have a different speeds in every test in the track. Your steering angle is not changed. That's what is neutral steer effect, which we have already discussed. So if that is so, KUS is 0. So when KUS is 0, it is simply L by R. So I would have my steering angle requirement in case the vehicle is of neutral steer vehicle, right? And that value is L by R. But my measurement of lateral acceleration would show with respect to this point. So when lateral acceleration is 0, L by R is what is my steering requirement for my vehicle. Would not be same as I do on a practical vehicle this test. So what would happen? My curve would be, as I have different speeds, I would have this is increasing, and at one point it would go to the maximum value. Later on again this would be falling down. Like this I would have my variation. So I can nicely fit a data curve here on this, and this is my. So every time I have a different speed, I have my lateral acceleration varies. So I would have my curve like this. So now it's very clear that what is the slope of this curve? I have to see. If the slope of this curve is 0, that means KUS is 0. Right? So what is the slope of this curve? What is on y-axis? Delta on y-axis. Lateral acceleration on x-axis. So dy by dx. So that's going to be d delta f by d of ay by g. So if I do that on this equation 1, what is that I get? L by R is constant, that's 0. So this will be simply KUS. So the derivative, the slope of this curve, what is obtained from the test, right, would be now given by this KUS. So when the slope is positive, so you can see here, the slope is gradually decreases and it is become 0 at this point, and it is parallel to this line. So let's say this point is maximum of this and point A, and here you have the neutral steer effect. So the vehicle would behave for any value of lateral acceleration less than this value as an understeer tendency vehicle, which is going beyond this is going to be an oversteer effect. So the vehicle which is originally an understeer vehicle can get into oversteer vehicle as the lateral acceleration value increases, right? That's what you should understand. So what is that you should understand? A vehicle can change its tendency from understeer effect to an oversteer effect at high lateral acceleration, high values of lateral acceleration, right? So that's what we should understand from this. So here this slope is positive, so KES is positive. Then you would have your steering angle requirement increases. And at this point, you see that you have the tendency is neutral steer tendency. So the lateral acceleration corresponding value of your same vehicle is behaving as a neutral steer effect, and then it is reaching to oversteer effect. So one can see that importantly, looking at this equation, right, KES, if I consider from my bicycle model, I would have for the given vehicle, for the given WF, WR and C alpha F and C alpha R, some constant value. So if it is positive, it is understeer effect. If it is negative, it's oversteer effect, and so on, we say. So if I take that, this is not going to be like a curve. It is going to be a straight line for an understeer effect, or oversteer effect with the same curve. It will be coming down and it will intersect here. You would have corresponding speed as a critical speed. That is mathematically to look at. Why? Because this has got a very important assumption that linear tire model. So these values are constant, and these loads are not varying. WF and WR are not varying, and then you are doing this. But in real time, though you are conducting a steady state test, you see that the vehicle has got flexibility. In bicycle model, it is a rigid vehicle. So when you have a vehicle as flexibility, at the beginning of the lecture, we have seen various design and operating condition aspects all are accounted. So your actual measurement would come like something like this. And that you are able to describe your vehicle tendency, and you are able to predict your lateral acceleration. So at that point is what is that point of separating, or point where the understeer tendency of the vehicle is getting into an oversteer tendency of the vehicle to torque on. So these are all possible in a real time when you conduct a test, right? Otherwise, you take this graph and you plot, you would see in digital assignment when you plot, for a chosen vehicle, these values are fixed, you have your KES fixed. So for that KES, you vary your U value and you plot this steering angle versus this. It will be a straight line. Three straight lines. One is horizontal line, one is a positive slope line, another one is a negative slope line. But in real time, when you conduct test, you get like this. So this is to be kept in mind. So this accounts all the effect of design and operating condition. Right? So this is one such test. So what is the other test? Other two tests are there. Another test is what is called constant speed test. So when I say constant speed test, that is U. So I'm going to have constant speed of my vehicle for different radii. So how this test is conducted, this is done on. So it is done at different turning radii. So I have a different circular test track of different radius. So I have the same speed of my test vehicle run on a different tracks of my circle, where I have variation in my radii. So if I have that, what all that I would measure? What are to be measured in this test? So one is, of course, the steering angle, because I look at the requirement of steering angle as the variation of lateral acceleration. So I also require to measure lateral acceleration AY by G. AY by G. So if you look at that, now let us look at our fundamental governing equation for steady state cornering, that is L by R plus KUS into AY by G. Right? So in this, let me take AY by G out. So if I take AY by G out, what is that I'll have here? GL by R into AY. And within bracket here I would have plus KUS, right? So if I take AY by G like this, so if I multiply inside, I get L by R. If I multiply here, I'll get this equation. I just do it like that. Why do I do that like this? Is to find out, this is my steer angle at front axle. So this, so delta F by dAy by G. So why do I require this? Is to look at in my measured lateral acceleration, the requirement of steering angle. So here AY by G, if I take, how is my graphs are going to come, measured graph. So if the vehicle happens to be of neutral steered effect, so for example, see if I differentiate this with respect to my lateral acceleration, I get the slope of the curve what I have. So that is going to be here it is GL by R into AY, and this is KUS. KUS here is constant for a given one, so that is sorry, see this is I have taken out AY by G, right? So this is inside. So what is that? If I do this, I will get this plus KUS is what is my slope. So now you look at the slope is different for constant speed test. Whereas in constant radius test, what was the slope of the curve? Constant radius test, slope of the curve is KUS. Now constant speed test when I conduct, I get delta F measured and AY by G measured through an accelerometer. Or I can use rate gyro, get R and multiply by forward speed, I will get this. So either way you can do this measurement. So we look at now lateral acceleration. You measure these two, and on the slope of the curve what you get from plotting this, because here you have a different radius. In previous case radius is same and speeds were different for every steady state run. So now for every steady state run you have a speed is constant but radii are different, so you get your requirement of steering angle when you had a different radii track when you conduct this test would be different. So those results would be something appearing like this when I measure. So this would be the plot that you get. So if I join them nicely, I would have, this is my variation of this. But in this, what is that you should see? So it would go to a peak value and then it would again drop as this is. So there would be a point where you see here is again having slope 0. So what is the meaning of this slope 0 point? So this GL by R into AY plus KUS is 0. That's the meaning, right? So what is my KUS? That's going to be minus GL by R into AY. AY is nothing but U squared by R. So this RR goes, it is U squared. So if where U squared is, what is that constant speed in this test? So if I take U squared on one side, this is minus GL by KUS. KUS. So you see that's very interesting now. What is this U here is U critical. Critical. So U critical is under root of minus GL by KUS. Minus GL by KUS. So this is going to impose that KUS value is negative to get this critical speed. When KUS value is negative, that is vehicle oversteered vehicle. But this point is what is the speed corresponding to or the lateral acceleration corresponding to the value when you would have your vehicle this side it's stable or on this side it is unstable. beyond this or at this lateral acceleration value where you have the slope of this measurement for constant speed on different radii. Every test you are changing the radii and you get your lateral acceleration. This is the curve. You would have a slope 0, and that slope 0 point is what is corresponding to V critical point. So this is going to be U critical square by GR. So that is the value of my lateral acceleration here, right? But now, when you say this is that vehicle to be of an oversteer vehicle, right? Oversteer vehicle here, and this is an understeer vehicle, stable. You can also see that what would happen if KES is 0. So if KES is 0 here, the slope is having the value of GL by R into AY. So that is the slope. So there is a constant slope of GL by R into AY, right? When KES is 0. So what is also otherwise the meaning of KES 0 for a neutral steer vehicle, irrespective of the speed, you would have the same turning radius. That's what you are physically when you say whatever may be the speed on a track, you would have the same steering angle, right? That's what you have seen in a constant radius test. So now the radius is different, so that value here going to be changing. See how is it going to change if KES is 0, that refer to neutral steer tendency of the vehicle or a neutral steer vehicle. So your slope here d delta f by d ay by g is going to be only GL by U square, GL by U square, right? Because RR goes out, I have this GL by U square. And your speed is constant, right? Constant speed test it is. So when speed is constant, G is 9.81, wheelbase is constant. So this entire thing is a constant value. So the slope is constant, and that slope is positive slope, and your vehicle would be having the slope something like this. So this refer to neutral steer condition, and this slope value is what is given by GL by U square. And this test is constant speed test, so the U squared also is constant here, it's not varying. So you have this. So now in this car, if I plot a slope, if I plot the slope here parallel to this, what is the meaning of this? Parallel to this, I would have the slope value greater than the slope of a neutral steer vehicle, that's of understeer behavior. If I have a slope value lesser than that of a neutral steer vehicle, so till here you see the slope value is more. After that, the slope value, this curve is coming like that. The slope here, whatever that we have, is lesser than that of the neutral steer vehicle slope. So from here onwards, the vehicle tendency is oversteer vehicle tendency. From here onwards, the slope is different. It is oversteer vehicle, but this oversteer vehicle makes your requirement of steering to reduce. At critical speed, the steering requirement becomes 0, and the vehicle gets into an unstable state. So you want to maintain the stability. What you have to do here is this slope should not be negative, or should not negative, should not be less than that of a neutral steer condition. So you have to keep reducing your steering so that this curve would go like that. But this is a test conducted. You are not, this is a steady state test. So you would be interpreting like that. So when the slope is greater than the slope of neutral steer condition, then that is for understeer vehicle from here, understeer tendency vehicle. And if the slope is smaller than this, then the vehicle transition from understeer to oversteer that take place, and you keep having your speed in every test is increases at one particular speed that happens to be critical speed. When the slope is 0 in this case, and that defines this, which we have already seen in our discussion. So this is what is at all can be interpreted to talk on vehicle handling characteristics. If I have my constant speed test is conducted. Interestingly, you also have another test. So what is that test? That is constant steer angle test. Constant steer angle test. So if delta F is constant, right? So you know that if my vehicle is of neutral steer vehicle that I have in steady state, whatever may be the speed I accelerate or if I accelerate or decelerate, there is a transient effect that comes into picture. So if I have my steady state motion in a curve with the different speeds, my steering angle is constant, would have the same radius turn is possible. That's what is for a neutral steer effect that we have seen, right? So that statement, how can you bring in? So let's again look at for that purpose a fundamental governing equation of steady state motion, right? That's delta F is equal to L by R plus KUS into AY by G. AY by G. So in this, now I wanted to have my so what is the right response parameter that would be good to look at? Curvature is what is the right response to look at it. So I am going to plot the measurement obtained from this test. One is the curvature variation as a variation of how does it vary as function of lateral acceleration. So that's what I'm going to plot. So here what are measured? Of course, the measurement is AY by G. AY by G is measured at constant steer angle test at various speed. At various speeds. At various speeds. Right? That is the measurement. So from the test result, the curvature 1 by R can be calculated. How can you calculate? I have my lateral acceleration measured. So I know lateral acceleration AY by G is what is U squared by GR. So I require 1 by R. So 1 by R is going to be AY by U square. GG goes out to AY by U square. So whatever AY that I measure, divide that by speed squared, forward speed squared, I get my curvature. So this would be obtained. So what do you mean by curvature? If the vehicle curvature increases, that means turning radius decreases. The vehicle is of oversteer tendency vehicle. If my curvature is decreases, the turning radius is increases. That means that is of understeer tendency vehicle. That we know, right? So let us now look at for 1 by R. I require 1 by R. So what I can do, I can take L out and bring that in this side. So it's going to be delta F by L. My governing equation would be modified like this. And this is going to be 1 by R. And this is going to be KUS into AY by GL. So if I take L and multiply inside, I get back my this equation. So I require curvature. So 1 by R is going to be delta F by L minus KUS by L into AY by G. Right? So this is the expression for curvature from the steady state governing equation. So this is the expression of curvature. So what is the variation of this curvature as a function of lateral acceleration is what is plotted. So if my vehicle happens to be a neutral steer tendency vehicle, KES is 0 here. So when KES is 0 here and I will have curvature is equal to delta F by L. Where delta F is constant as this test is of constant steer angle test, right? So I would have delta F by L which is constant, and that is why this curvature will not change if the vehicle is of neutral steer vehicle. and the value of curvature would be given by delta f by L. Delta f is that steering angle which is maintained constant divided by wheelbase of my vehicle would give me a constant curvature value irrespective of my lateral acceleration variation if the vehicle is behaving as a neutral steer vehicle. So is that point clear? Yeah. So if that is so, now what all my measurement, I would get my curvature of this at different speeds that you are conducting. So I would have, so here there is no track, is not a circular track. It is a flat, large track, skid path. So you are able to go with the constant steer angle. So when you go straight and you give a constant steer angle and you maintain steady state motion at a particular speed, what would happen? What would happen? You get your turning radius. So you mark that turning radius. Again, you mark the turning radius. If that turning radius is not changing, that it is of neutral state vehicle. But in real practical vehicle during the test, it won't change. You would have this curvature decreases as the lateral acceleration increases for some time. And it is going to change its value like this. So this is what is that you would get your test results as. So I can have a nice fit on this so that I can look at the slope of this curve. So slope of this curve is what? D1 by R by dAy by G. So that's going to be, since the delta F by L is constant and that goes out, and I would have here minus KUS by L is what is that slope. So it is KUS by L is what is the slope. So we know that if KUS is 0, so this is what KUS is 0, neutral steer condition. When KUS is 0, you have it is given by slope 0. So slope is 0 for that. So I can just draw a line parallel to this horizontal line, or draw a line corresponding to slope 0. That's a horizontal line for this curve. So this is the point where your vehicle, which is of understeer vehicle, would change into an oversteer condition as the variation in your lateral acceleration. So at this particular lateral acceleration is the wedge point, the point where understeered behaving vehicle can change into oversteer vehicle. And you see that's very interesting to look at the slope. So I have the slope is minus KUS by L. So when I say this understeer effect, the slope should be here negative, right? So this is negative slope. So this slope here, what I have is negative, so that you should have KUS value positive. So when KUS value is positive, KUS is positive, you would have negative slope as per this equation here. If this is positive, if KUS value is negative, then the slope will be positive. So slope is positive here on, right? So here KUS value is negative. So that's very clear, right? So negative slope here corresponds to an understeer effect, as the slope here is negative. So KUS value should be positive to have a negative slope, and that is what is corresponding to understeer tendency of the vehicle. And the KUS value is negative to have the positive slope here, right? And that is what is an oversteer effect. So this is the point where it is just separating both as a neutral steered condition of the vehicle, right? So these are all some of the interesting pre-tests that are generally conducted by OEMs on the different vehicles, employing this sensors, that is to measure your steering angle, that is to measure your lateral acceleration, or to measure your yaw velocity. So we can also have this variation as function of yaw velocity. But why lateral acceleration is preferred is because under high frequencies, the lateral acceleration is approaching constant value, whereas yaw velocity response would approach 0. So generally it is preferred to measure lateral acceleration. But one can have the lateral acceleration value just from the rate gyro value also that we have looked at from the kinematic relation, right? So if you multiply your R, that's a relation that we have seen. What is that? R into R is what is U. So AY is what is U squared by R. So if I have R by R is R, I multiply by forward speed. So yaw velocity multiplied by forward speed would give me lateral acceleration. Or if I measure lateral acceleration, I want to get yaw velocity, then I should simply divide that by, I measured this and I wanted to have, I measured R. I have to get my lateral acceleration. What should I do? I should multiply this by U square, right? Is that right? So just let us write. So AY is what is U by R, that is R into U. So if I measure AY divide by U, I'll get it. If I measure R multiply by U, I'll get lateral acceleration. So that is how you can do this, any one of the measurement. So now here, out of these three tests, if you want to compare, you would always say that, what is that? Just a minute. You would always say that the test one, constant radius test, is the simplest and requires little instrumentation. You require to measure only delta F and U. Forward speed measurement also sufficient in case of constant radius test, right? So out of this, test 1, U constant, right, is a, sorry, R radius constant test, right? This first test, what was that we discussed, is a radius constant test. Turning radius is constant, is the simplest test. It requires a measurement of delta F and forward speed alone also sufficient. Why? Because from the forward speed you would be able to get your lateral acceleration, AY. Because this variation forward speed, see, maintaining that is difficult. This AY can be now related to this with the U squared by R. So if I know my forward speed measured, U squared by R, turning radius constant, I would get my lateral acceleration. Right? So that is why this is the simplest test. Whereas the second test, U is constant, speed test constant on different radii, is a practical test, is a practical test of the vehicle, as the vehicle responsiveness is well understood under the steady state condition, so constant speed condition. So that is normally the preferred test. So this is so the test 1 is simplest test to talk on this vehicle cornering behavior. Test 2 is preferred test, as it is that practical test that we say, as a driver usually maintains more or less the constant speed during the turn, and the steering wheel by the required amount to negotiate the curve can be felt by the driver. So that is why this test is always better test than this. So what is my third test? The third test is a steer test, steer angle constant test that we have seen. When this is constant, it is easy to execute. This test is easy to execute. So I would have my steering angle every time fixed, and then I would do the test on a very large skid pad. But however, it requires the measurement of lateral acceleration, yaw velocity. So this requires measurement of lateral acceleration or velocity, or right. So these are all that the test requirement and the preference of test that can be considered for handling characteristic prediction. So any doubts so far what we discussed? Any doubts?
No, sir.
No doubts.
No, sir.
Yeah. So if you look at, also there is another diagram called handling diagram, right? Handling diagram. Handling, L-I-N-G, handling diagram. So what is this handling diagram? It is also again a popular diagram. Drawn out of a test, and that test is again a constant steer test. So let us just look at that test, how it would be, right? So some more points that we will discuss and we'll stop today's class. Yeah. As at the beginning of the lecture, I was telling you the limitation of our bicycle model. As this model is a rigid vehicle model, there is no suspension effect considered. So there is no role of your sprung mass relative to one sprung mass and so on. So that would not going to exactly predict the exact variation in your understeer gradient value. Why? Because the bicycle model, what we consider is primarily depends on the values of normal loads in the axle and the cornering stiffness of the tire, the understeer gradient value. So that is sufficient enough to compare under the steady state condition, but it is having its limitation as those values are going to be changing with respect to the design aspects of the vehicle and the operating condition of the vehicle. That is the reason why these all physical tests were conducted in order to have a realistic cornering behavior prediction. That is that we understood at the end of this lecture. And if you look at that, you see there are vehicle, before going into the handling diagram, the vehicle design aspects wise, if you look at, let me just give you this plot, which is also available in your Wong textbook. Look at that later. So I have my AY value varying. So here till say 0.5 G value, correct? 0.5 G value is marked. So it's 0.4, 0.3, 0.2, 0.1, 0. So this 0.5 G is what something a limiting factor is considered most of the passenger car segment. There are a plot of variation of this KUS. So why there is a variation of KUS is you understood. So KUS is constant is what we take it in our bicycle model, right? So if you have your parameters load, cornering stiffness constant, you get this, and then you say that negative means it is a oversteered vehicle, positive means an understeer vehicle, 0 means neutral steer vehicle, you are concluding. But that is mathematically when you look at with the limitation of the model. But we understood today this KES value can vary, because the KES value can vary that make your vehicle which is otherwise an understeer vehicle to change into an oversteer condition, and that depends upon your lateral acceleration. So if you see that there are 4 class of vehicles and their variation of understeer gradient as the lateral acceleration varies are given. So here you see that's 0. So when you take a 0, that is K is 0 is neutral steer condition, right? So I take here values -1, it's given in degrees, -2, and so on, and this plot goes like this, and here it is 1, 2, 3, all degrees. So it can be in radians or degrees, right? 4 degrees and so on. So this, if you look at, I will draw the variation of KES goes by this. I call this as 1. So this 1 here is the observation of a vehicle which is front engine rear wheel drive car, front engine rear wheel drive car, which is usually conventional. Any vehicle you see, we have our engine in the front and the differential in the rear. So rear wheel drive car. So you see your understeer gradient value keeps increasing as your AY value increases. What do you mean by that? What do you mean by that? Understeer gradient value is increases positive and positive. That means it's going to be more understeer effect, more ruggish, that you require more steering angle to have. So this vehicle will be always stable vehicle. That's the meaning of it, right? As you have a variation in lateral acceleration, understeer gradient value increases, and it is going to have these values like this. That's going to say that you require in hard cornering more steering angle to be given for the turn, and it is more and more ensuring the stability. Though the vehicle steering effort is requirement is more, which can be compromised or can be employed through power steering and so on in our vehicle. So that's one. So if we look at another vehicle, which is an European vehicle, European front engine, European front engine, front wheel drive vehicle, front wheel drive car. If you look at that, variation is also similar to that, but you see that is going to have sometime gradually, it's going to have a neutral steer tendency, then the slope is going to be like this more. But again, that is going to be as the lateral acceleration increases, though it is neutral steer vehicle. Neutral steer vehicle is more responsive vehicle for your steering input, right? Understeer vehicle is least responsive. As more and more understeer gradient, it is more and less responsiveness vehicle. More and more oversteered vehicle is more and more sensitive vehicle, we call it. So the word sensitive and responsiveness to be used whenever you say that the vehicle tendency deviate from its neutral steer effect, right? Yeah. So this is its nature. So if you look at another car, which is European rear engine, rear wheel drive, European rear engine and rear wheel drive car. You see that vehicle has got more or less with this neutral steer tendency, slightly it is varying, but at particular limiting value of lateral acceleration, it falls to oversteer tendency. So this is this. So European rear engine rear wheel drive vehicle is more of no compromise with the sporty vehicle. So you have a thrill of good responsiveness because the neutral steer condition is a very good vehicle, right? But that is maintained for lateral acceleration almost of 0.5. After that only it falls and it changes into your overstay tendency. So as you see, the more and more lateral acceleration, more and more critical speed is decided. So more critical speed means you have a range of operating speed with a very sensitive in steering response possible for such vehicle, right? And the fourth vehicle, if you look at, it's very American vehicle. They are always preferring to have oversteer tendency vehicle. So this is American rear wheel drive vehicle. American rear engine and rear wheel drive car. That tendency, if you look at, it is coming below like this. That means you have oversteer tendency vehicle. This is oversteer tendency vehicle. So this is fourth one. So these are all some of the results, observation published by the researchers, the OEMs, to compare the handling characteristics of your different vehicle. And this diagram is not called a handling diagram. So handling diagram is the diagram, is a plot where you have your lateral acceleration ay by g versus ay by g versus so what is written first will be on a vertical axis. So far we have seen ay on the horizontal axis. So ay by g versus a parameter what is called L by r minus delta f. L by r minus delta f. So if I plot this, and that is what is called a handling diagram. That is what is called a handling diagram. Right? So that diagram would appear like this. And another 2 minutes we will finish the class. So I have my vertical axis. In that I have my ay by g. And how that is going to vary as function of this. So L by r minus delta f. L by r minus delta f is what is on this axis. So L by r can be replaced by RL by u as well. So L by r can also be replaced by RL by u because r into r is what is u, right? R into r is u. So yaw velocity I measure, wheelbase is geometry, u is that speed, right? So if I have that, steering angle is constant. Delta f is constant. So constant steering angle, if I have this, I can also replace this L by R by RL by U minus delta f. So if I take that, I would have my plot varies something like this. So the lateral acceleration value would vary like this. So how do you interpret that? What is the slope of this curve to get what I should do? My y-axis is this, x-axis is this. So dy by dx. So I have to get d ay by g by d of this RL by u minus delta f. So this variation slope I should get to talk on this graph. So this graph, this plot is obtained how? For varying this parameter L by R is constant minus this varying this parameter. So how this parameter is varying? Because the L by R is replaced by now RL by U. In steady state R is varying. R is what is the orientation change. So if I take that RL by U, there is a variation here, and that to vary as per my lateral acceleration. Right, so the slope of this, if you look at, is infinity at this point. So the slope here is infinity. Dy by dx is infinity. So how do you get that? So simply you have your steady state equation now again. So delta f, let me take it here. Delta f is what is L by R plus KUS into AY by G, right? So what do I want is L by R minus delta f parameter. So if I want that, how do I write that? KUS into AY by G, and I'll bring this on the side, and I take as like this L by R minus delta f. So delta f minus L by R is what is written now like this. So now I have this equation. So I can just do this, right? So in this I can rewrite this as ay by g, ay by g. This side it's going to be minus L by R minus delta f by KUS. So now the slope is going to be what? Dy by dx. So dy by g by this parameter, that is going to be 1 by KUS, minus 1 by KUS, right? Minus 1 by KUS. So when KUS is 0, that is what we call it as the neutral state effect, that the slope is become infinity. That is what is corresponding to this vertical line. Slope drawn here. So this is what is your neutral steered effect condition. So it gives you the two zones. So one here is the negative slope. So this is negative slope. When this is negative slope, KES is positive. So here it is understeered effect. See, I have to have here this slope is negative. KES value should be positive. If I have to have this part of the curve as positive slope, for that KES value is negative. So this is going to be an oversteer tendency vehicle. So that is how you would say. So from this diagram, if we have your lateral acceleration below this variation, this is referring to understeer tendency of the vehicle. Or if this lateral acceleration increases, the understeer tendency is changing to a oversteer tendency from this point, whereas this point corresponding to neutral steer point. So this diagram is popular diagram again, called handling diagram. So this is what is called a handling diagram. So tomorrow that you are joining OEM and you are with your testing team and you do this kind of test, so you should be very much conversant to look at the tendencies. So there the test driver is an expert driver. He is an evaluator. So you would say that this vehicle is a understeer tendency vehicle, oversteer tendency vehicle, fine. You would give a comment. But you have to, as a researcher, as a test engineer, when you come back and work, you should be quantifying it mathematically with the parameters. Then these tests, what is today's class that you have learned, are quite useful, and you have to revisit at that time. Once again, these lectures are the textbook Wong or any other standard textbook for handling, to refer back to be very competent in your profession. So with that note, let me stop today's lecture in case you do not have any doubts. So can I get any doubts from your side?
No, sir.
No doubts. Is it clear?
No.
So you would have examination question based on this test, your understanding. So there are many plots that we have drawn, how those plots come, how those slopes are defined. Based on that, how do you talk on the tendency of the vehicle, and that helps you to characterize the behavior of a vehicle during cornering. And these all are very important part, right? So I just downloaded your attendance. Since there are no doubts, we will stop at this point of time. And tomorrow, as I said, we will meet again at 2 p.m. Tomorrow, Tuesday, you are free. So I would send the the schedule link to have a lecture tomorrow, 2 p.m. Tuesday. Is that fine? Any response? Ragis?
Yes, sir.
Stanis?
Yes, sir.
Yeah. So tomorrow,
Yes,
2
sir.
o'clock, you are free. I just have seen that from the free slot time. So we would have the class at 2 o'clock tomorrow, right? Yeah. Good day to all of you. I will stop recording at this point.